The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Go ahead and start introducing our next speaker, who is Tom Howe. He's going to talk to us about the commissioning aspect. Once again, one of the unusual things about our code in comparison to most of the other codes that we have within ACI. Tom Howe has 31 years of experience in pressure vessel and storage tank design and construction with KBR and Chicago Bridge and Iron. Tom has been with KBR's Vessel Mechanical Technology Group since 1990 and has been working with KBR's LNG Technology Group since 2001. His current role as LNG tank engineer includes tank sizing and spacing studies, generation of tank specifications, scope of work definition, preparation of tank subcontract bid packages, technical evaluations of proposals, review of technical drawings and calculations, and construction support. Tom is a civil engineering graduate of the University of Houston and is a licensed professional engineer in the state of Texas. Tom is a member of the ACI 376 committee, as all of our speakers have been here today. Very active member. And Tom, please come on up and welcome you to give us your presentation.
Good afternoon. ACI 376 Chapter 12 covers various aspects of commissioning, goes through testing, pressure and vacuum testing, nitrogen purging, the tank cool down, settlement and movement monitoring, LNG tank fill methods, decommissioning, record keeping and nameplate. And we won't go over the record keeping and nameplate anymore, but I'll go through most of the other issues here. Testing for this, what's written into the ACI code is testing of primary tanks where the inner tank is made from pre-stressed concrete. Where you have a metal inner tank, that's covered by other codes. API 620 would cover that. So testing of the primary container for leak tightness is required using either visual inspection at hydrotest, local pressure vacuum testing, or NDT methods. Now, typically a hydrotest is used for testing the leak tightness of the inner tank. Possibly above the hydrotest level, you can use the other methods. Hydrotesting is required for the primary containment up to the design liquid level where the foundation conditions permit, but not less than 1.25 times the product load. So you want to test the foundation up to 25% overload. For metal tanks, sometimes they have a reduced hydrotest level due to limiting the steel thickness based on the product load rather than the hydrotest load. But for a concrete tank, it should go up to the design liquid level. And then testing for the leak tightness of the secondary containment is normally not required. Nevin had mentioned that's typically, it's only a spill condition that should never happen, so testing for that leak tightness of the secondary containment is not done. If it was to be done, it would take a lot of special effort to do it due to the insulation inside the tank and arrangement of the tank. All right, testing considerations. Normally performed after the specified strength and age are reached, performed after pre-stressing and grouting are completed, performed after the QA testing of the concrete. Shall not exceed 30 days unless agreed by the owner. It's best not to keep water in the tank for a longer period. If you use a seawater hydro test, just like for a metal tank, you want to use a freshwater spray to eliminate any corrosion issues or problems. Any attack of the concrete due to the seawater hydro test. Hydro test shall conform to the water quality requirements listed in the code. Shall also conform to corrosion protection requirements. And then after the hydro test, cleaning and drying would be required. Okay, pressure vacuum testing. Here we're talking about the outer containment, where the inner tank contains the liquid, the outer tank contains the vapor, and has to be pressure tested for 1 1/4 times the design pressure. And that design pressure, 1 1/4 times the design pressure needs to be held for at least 1 hour. And then the test pressure is reduced to allow for inspection for leaks. In addition to that, the pressure and vacuum relief valves are mounted on the tank and tested. And the code also talks about the pump wells, which are tested to the piping code. Okay, after the tank is hydro tested and pressure tested, the tank is purged into service. And the idea here is to eliminate all of the oxygen in the tank to a certain level, make sure that the tank is dry. A complete procedure needs to be prepared for the purging operation. Oxygen level to be 8% or less. Tank to be dried with no standing water. Inner tank is purged first, followed by the annular space. And it's completed when the oxygen level is less than 8% and the dew point below the required level, and held for 12 hours. And then the tank will be held under a nitrogen purge until time to cool the tank down and go into service. All right, the cool down, for the cool down you need a complete step-by-step procedure which tells you who does what are the assignment of duties, what is the source of the cool down gas, is it the product or is it nitrogen, liquid nitrogen, depends on what RLG is being cooled down. And then also the cool down procedure should have cool down rates, temperature limitations, those type of things. And for LNG, typically, if LNG is not available, they may bring in a ship, or it may may cool down with nitrogen. In any case, a procedure shall be set up to do that. All right, settlement, movement, and monitoring. Differential settlement of the foundation before, during, and after the hydro test, and at the first fill of RLG shall be monitored. And also, that was the level monitoring system that Mike had talked about in his presentation. Also, monitor the inner tank lateral and rotational movement for use during and after cool down. So this is something different, where you have to have some type of instrumentation inside the tank to be able to tell if the inner tank has, when it cools down, what the movement is, as well as if that tank has rotated at all. All right, 12.7 is the filling methods. Typically LNG for an export terminal has a splash plate at the top, a connection at the top that allows for filling LNG at the top, where you're not worried about stratification of the LNG inside. On import terminals where you have different densities of LNG that might be brought into the tank, or long periods of time where LNG sits in the tank, typically top and bottom fill are provided. And you can see the different types. Top one has just a general arrangement with the splash plate at top, and the other one has is able to distribute at the top as well as have an opening at the bottom where LNG can be rotated through the tank. Okay, and that was it for the commissioning portion that I was going to talk about. Does anybody have any questions?
Tom is also going to got some construction slides that he's going to present. So one thing it's kind of interesting. I'm getting into LNG and I see this picture of the ship. Has anybody seen the LNG transport ships? Of course, it's kind of interesting because you might not notice, but there's actually like 4 pods, and these pods are actually the LNG storage tanks. I was bidding a big wastewater treatment plant in Boston, Deer Island, which had egg-shaped digesters. And we were doing it in concrete, and there were some others doing it in steel. And the winning solution for that bid was actually a firm that built these types of pods, and they did that same type of technology for an egg-shaped digester, which is for wastewater treatment. And they physically built them down in South Carolina and then barged them up on site. So it's interesting how you get an overlap of technologies and things that happen in water, wastewater, and LNG. We have some different loading considerations because of temperatures, obviously, but when I see those ships, it's kind of interesting, and I thought I'd point out to you that it is a little bit different than some of our petroleum oil tankers. So let me load the next part. Actually, you have a video too, right? I think maybe to go on schedule, what I'll do is start his video, which is actually construction.
It's construction of an LNG fuel containment tank, kind of time lapse from the beginning to the end. This was a project in Qatar that KBR built, and Mitsubishi Aviators was the tank contractor.
LNG, liquefied natural gas. As the world becomes more environmentally conscious, demand for LNG as a clean energy source continues to grow. LNG is stored in LNG tanks at shipping and receiving terminals. As a manufacturer of LNG tanks, Mitsubishi Heavy Industries, or MHI, has completed more than 30 LNG tanks since 1977. These LNG tanks in Qatar were constructed by MHI. The Middle East, the Persian Gulf, and Qatar. In this land of intense heat, MHI has completed 3 state-of-the-art LNG tanks. Ras Laffan LNG recognized our technology, experience, and proven track record. In 1995, the company awarded us a contract covering design to on-site construction on a full turnkey basis. Construction began in 1996, with 2 tanks completed in 1999 and the remaining one in 2000. Since the award of the contract, we have undertaken the design, procurement, fabrication, and construction of tanks with a capacity of 140,000 kiloliters under the plant EPC contractor JGC Kellogg. Now let's take a look at the construction of LNG tanks in Qatar. Construction of LNG tanks begins with foundation work. The ground condition here in Qatar required piling. Over 400 piles are being driven into the ground to support tanks. After the piling work, the base slab construction is begun. The load of the fully filled tank is 120,000 tons. The slab plays an important role in distributing this load evenly over the ground. The base slab work is followed by concrete wall construction, which is done concurrently with roof assembly work on the slab. After 6 months of construction, the concrete wall is raised to as high as 40 meters. Meanwhile, the roof is assembled at the bottom of the tank, surrounded by the concrete wall. The work process is optimized by carrying roof blocks in the tank. These roof blocks are temporarily built beside the tank. While the roof is being built, an aluminum suspended deck is placed beneath it, where the insulation material is to be mounted at a later stage. The tank wall being built here uses pre-stressed concrete with extremely high rigidity. Ducts are run through the concrete during pouring, and then cables are run through the ducts when the wall is completed. By providing a set tension, the rigidity of the concrete structure is increased. The cables are installed in both the vertical and horizontal directions of the wall. When the concrete wall and the roof are completed, the roof is raised to the height of 40 meters using a technique called air raising. Air raising lifts the roof very slowly. This work continues over about 2.5 hours. The roof is fixed when it is raised to a set position. When the roof is fixed, concrete is poured on top. Next, a platform is constructed to mount the piping. Inside the tank, inner tank work begins. The inner tank stores LNG at minus 162 degrees Celsius. For this reason, it must be made to very exacting standards. We take our utmost care to ensure the quality of welding. All welders must be thoroughly trained before they can work on a real tank. Here, workers concentrate on the work they are about to begin. The inner tank is made from a special material, which is 9% nickel steel. One by one, the pre-rolled steel sheets are brought through an opening into the tank. The delivered steel sheets are hoisted and placed in a specified position. The inner tanks in Qatar have a 10-layer structure. The construction of a tank combines many complex tasks. While the inner tank work is underway, many different tasks are also going on outside the tank, such as piping, external stair construction, and coating. Tank construction involves more than 800 people from over 10 countries working simultaneously. Particular attention must be paid to safety. MHI assigns a dedicated safety supervisor to work closely with the people on site to ensure that no accident occurs. During the inner tank work, insulating and construction at the bottom of the inner tank are also going on. When the work inside the tank is completed, a hydrostatic test is performed. The tank is filled with water to check mainly ground subsidence. Now the final process. Pump installation is underway. Before putting the tank into operation, an O2 purge is performed. All the oxygen is forced out by filling the tank with nitrogen. A vaporizer for the liquid nitrogen is placed on site. This is the completed tank as seen from the platform. The enormously complex project required over 3 years of work, but now another high-quality tank is complete. In Qatar, we built 3 tanks of this type in succession. The Ras Laffan LNG tanks in Qatar, built by MHI. From these tanks, LNG is shipped all over the world. Our project execution ability was proven by the construction of these tanks. Based on this performance, MHI will continue to build LNG tanks around the world, contributing to a clean and stable energy supply for our planet.